Now that we have successfully determined the shrinkage losses and the losses due to the steel relaxation, our next step is to determine the creep coefficients so that we can proceed with the substitutions of the other parameters. Referring to this slide, the creep coefficients is determined by these equations, which is subsequently need to compute this equation. This slide demonstrates the computations of this creep coefficient. We require phi RH, which referring to this slide, it is governed by the FCM. Therefore, we will need to first calculate the FCM. The FCM is calculated from these equations. FCK plus 8, which is equals to 48. X number is greater than 35 megapascal. Then we know that we will need to use these equations to compute the phi RH, which is this equation. Within the equations, there is relative humidity, which is given in the equations as 60%, and there is a H naught here. It is calculated from these equations, the area of the sections divided by X perimeter, which is calculated here, and there are factors of alpha 1 and alpha 2, which can be calculated from these two equations in the functions of FCM. Substitute FCM into the equations here, you get alpha 1 and alpha 2. Then you are able to obtain the phi RH, which is equals to 1.569. Next, in these equations, there is FCM. You can substitute 48 here, and you will need to determine the T naught here. For you to determine the T naught here, this T naught transfer will be taken as 3, and there is an alpha here which you can refer to the table here. Type R is being used, therefore the alpha will be equals to 1.0. Substitute into the equation here, you will get T naught equals to 7.706. Now you have this phi RH and T naught obtained. Substitute into the equations, you get this creep here equals to 2.83. The creep that we have obtained is from here, which need to be later multiplied with a factor of K sigma that are governed by the conditions of the ratio, whether it is greater or less than 0.45. With that, we will need to compute this sigma C T naught and also FCM T naught. The FCM T naught here is determined from the equation here. The T here represents 3 days when transfer is done, and the S here will have to refer to a table. Type R is being used, therefore the S will be equals to 0.2. Substitute into the equations, you get 31.8. Now you need to determine sigma C T naught based on the equation here. The pre-stressing force is 1200. The A, I, and E are the geometrical property of the section, which is 13.7 Newton per mm square. The ratio of this is equals to 0.43, which is less than 0.45. Therefore, the K sigma will be equals to 1. Your creep coefficients will be 2.83 multiply 1. Now that in these equations you have obtained the creep coefficient here, you would like to next compute the creep, which is chi, based on the equation here. The equations for chi is here. which is in the functions of the modulus or elasticity of the steel divided by ECM for the concrete as refers to the equation here. FCN is FCK plus 8. Substitute into the value, you will get this, and APS will be N times the areas of the tendon, and the geometrical properties of the sections are given. In the questions, it is stated that the eccentricity will be the same throughout the sections, which is 450 mm. Therefore, the E here will be equals to 450. Substitute the value into the equations, you get chi equals to 0.199. Now that you have computed the chi here, you will need to next compute the sigma CQP, which is considered as the average of the stresses at the support and stresses at the midspan. The E at the support is 450 and the E at the midspan is also 450. The only difference between the stresses here will be the sigma C external, which is determined from the moment caused by the UDL, and the factor of safety will be taken as 1.0. Based on the GK and QK given, you know that the UDL is 19.2 kN per meter. The beam span is 12 meters. You can compute the M external from WL square per 8 for simply supported member. Then you get your M external. Your sigma C external will be determined from the equation here, which is equals to 7.01. And from there, you are able to compute the stresses at the midspan and also at the support. The P here represents 1200, and the average stress will be the average of the two, which is 10.21. With that, all the components of the equations has been found. Substitute all the equations and you get your total losses is 277.1 kN. So now let us look at the summaries of the result computed from the pre-tension member as a compilation from the previous examples. First, the member is a pre-tension. There will be no frictions and wobble and draw in of the wedges. It is purely governed by the elastic losses, which is calculated as 88.8 kN. In comparison to the pre-stressing force of 1200, the short-term losses constitute about 7.4%, which if you look at the examples in the previous chapter, it was assumed that 10% losses. The value here is less than the assumed 10%, and the number is considered close to 10%. Therefore, we will consider the assumptions of 10% is acceptable. Next, we will look into the long-term losses, which is found at the surface in the form of the summations of the short-term and the long-term losses. The losses that we have calculated just now represent the long-term losses as the summations of the shrinkage, relaxations, and also the creep. The total losses at the surface state will be the summation of these two, which is found as 30% out of 1200 kN pre-stressing load. In the previous example, we assume it to be 25% only. This number is greater than 25 and is far away from the assumed number. With that, in the calculation steps here, the section which is checked pass here within the stress limit, which at the end of the day found at the actual losses here far greater than the assumed value. Therefore, it is recommended that to recheck again the stress based on the actual value of the losses to make sure the section pass. Therefore, the checking of the stress limit for the serviceability limit state will be required for this case. Let's say now we take another example for a post-tension member with the eccentricity equals to 0 at the support and equals to 450 at the midspan. The tendon is stressed successively. Because of the tendon stress successively, there will be elastic losses, which is calculated as 41.8 kN. Due to the curvature of the tendon, and it is a post-tension member, there will be frictions and wobble and also drawing of the wedges. Let's say the losses are calculated here. The summations of the short-term losses here will be equals to 27.4%, which is much greater than the assumed value of 10%. That means we have already underestimated the short-term losses, and the assumed value is not acceptable. Definitely we will have to check for the stress limit for the serviceability limit state. As for the service state, the short-term losses and the long-term losses is to be summed up, and which is found to be 43.6% losses. It means that about half of the pre-stressing force losses at the service state, which is significantly high, and the assumed value is only 25%. This makes you will have to check for the stress limit. But looking at the number here, we realize that the losses is extremely high. Even though you check past the stress here, it will come to a state that the pre-stressing methods is inefficient. You are only able to use about half of the pre-stressing force at the end of the day. And it is likely that if you check with the actual losses here, since the value is significantly vary from the assumed value, which you propose the P and E and dimensions based on the assumed value, it is likely that the stress checking later to fail. When the stress limit is failed, if you would like to keep with the current conditions of the pre-stressing, you will need to repropose the sections, and most likely you will have to start all over again with the design of the pre-stressed member. With that, probably you will have to look into the mechanisms to reduce the total losses within the member. You found that the drawing of the wedges contribute a significant amount of the losses, which its effect can also be compound to the service state. Probably you would like to look into the mechanisms for the anchorage. Try to limit the degree of the drawing, and if you still found the actual losses is still relatively high, you could consider to redesign the sections so that it is possible to have the tendons to be stressed simultaneously. With that, you are able to eliminate the elastic losses, and these elastic losses can also be eliminated at the surface level. Through this, it is possible for you to significantly reduce the losses. This can likely to reduce the losses until to an acceptable level, which is close to this. If you find the actual losses is still greater than the assumed value, you are always recommended to check the stress. The stress limit is likely to pass if this number is close to the assumed value.